the definition of linear transformation. The definition of linear transformation and some other elementary properties of linear transformation. Okay. Now let us have to see here some other examples of on linear transformation. Okay. Just you have to see and one of the example here 3.3.2. Now let L equals to R square be the real linear space. Okay. Students, listen carefully. This is one of the important session on especially on functional analysis part. Third unit is bounded linear transformation. What is the boundedness? Okay. Already you have introduced in real analysis. Bounded concept is okay. Now, lower bound, upper bound, and least upper bound, and greatest lower bound. At the same time, that is also called, so least upper bound means LUB, that is the supremum, and greatest lower bound is called infimum of this part. Now, through the linear transformation, how to define the boundedness on functional analysis part. Okay. Now, here the L equals to R square. This is the two-dimensionality real linear space. Therefore, two-dimensionality means now given the defined the mapping is, what is the defined mapping? Just you have to observe given this problem. First of all, T maps R square to R square. Now, here the domain of the part is two-dimensional of this part and the codomain is also two-dimensional part. Now, here the defined the mapping on the linear transformation, T be any one of the mapping. Sometimes that is also called homomorphism on linear space. Okay. Now, here the two dimensions defined when the domain approaches to codomain, defined the mapping is denoted by capital T. Now, here just you have to observe this given the domain of the coordinates here x1 and x2. So, defined the mapping of the relation is T of x1, x2. Here, x1 is the first coordinate on the first dimension, x2 is the second coordinate on the second dimension. Therefore, x1 and x2 defined the domain of this part. We are taking the domain of the coordinate is x1 and x2. There are two coordinates given in this point. So defined the mapping of the relation. So first of all, so you have to observe this one. Defined the mapping. So given the mapping, just you have to observe the defined part. So there are two coordinates. So dimension is 2. And at the same time, that the relation is x2, x1, that is the codomain of the part. There are two coordinates that is also in the same manner, that is also two-dimensional part. So defined the mapping is T maps R square to R square. Now, when it is here, suppose here R cube is here. R cube means x1, x2, x3, there are three coordinates. And at the same time, this is also R cube. Now here, x3, x2, x1, define the image of the relation is there. So, both are equal is there. Define the mapping and define the relation. Both are coincides. Without equivalence, now given the defined the mapping is not a linear transformation. Okay. Now here the defined the mapping, then the relation is T of x1, x2 equal to x2, x1. Is it a linear transformation or not? Okay. Already we will prove that given the relation is a linear transformation from the relation. Okay. Now, just you have to, as an assumption, x coordinate and y coordinate, we are taking the domain of the values, put x equal to, according to that relation, x1, x2. And at the same time, y coordinate is there. Now, y equals to, therefore, y1, y2 is there. There are two domains, domain of the values we are taking on the domain of the part. Here, x equal to x1, x2, y equal to y1, y2. Here, alpha being any one of the real number. Then, what about the linear transformation condition? Transformation of x plus y. Students, listen carefully. What about the condition? Here the condition is transformation of x plus y equal to transformation of replacing the x and y values given this relation. Put x equal to x1, x2 and again y equals to y1, y2 is there. So this relation now must approach as T of x1, y1 plus T of x2, y2. Okay. Now, according to this is again, this value is x, this value is y. Okay. T or transformation of xy is there. Or transformation of, there are two coordinates. Again, this value is x2, x1. Here x2 is x2 plus y2 and x1 is, what is that? x1 plus y1 by defined of this part. So again, this can also be written as x2 x1 plus y2 y1. Again, according to the relation, x2 x1 is transformation of x, y2 y1 is transformation of y. So first condition is verified. In the same manner, transformation of alpha x, that is transformation of alpha of, replace already assumption of this part x equal to x1 x2. Again, it can also be written as transformation of alpha x1 and alpha x2. Okay. Now this is x1, this is x2 is there. Our assumption, this is the x1 coordinate, this is the x2 coordinate. According to that relation, transformation of x1 x2 equal to x2 x1. Here x2 is alpha x2, x1 is alpha x1. Again, alpha being the common of this part, that is the scalar, that is alpha of x2 x1 is there. By the relation, from the relation of this part x2 x1 is transformation of x is there. So when the both conditions are satisfied, that is called T is a linear transformation of R square into itself. So given the relation is satisfied according to their two conditions, that is transformation of x plus y equal to transformation of x plus transformation of y, transformation of alpha x equal to alpha into transformation of x. Again, just you have to see the 3.3.3 example is here. Okay. N is greater than 1. Suppose if n being the integer, that value being the integer means the natural number, here then it must be greater than 1 is there. Put L equal to on the linear space n dimensional of the real system. So m dimensional of real linear space L and L dash. So define the mapping L to L dash means R power n to R power n minus 1. That is the transformation of the relation. Given the defined mapping is the relation T maps R power n to R power n minus 1. This is the n dimensional of linear space. This is the n minus 1 dimensional of real linear space. Here, n is greater than n minus 1. Just we have to observing here. So, given that relation, here we are taking the n dimensional of the values is x consisting of this part, x1, x2, so on, xn. That is the n dimension is also coincides here. When the image of this part, image of the dimension is n minus 1. Now, in the same manner, replacing of the x consisting of the part x1, x2, so on, xn minus 1. So, this is the relation and it depends upon the mapping. Now, this is also a linear transformation from L into L dash. Here, L means n dimensional of the part, L dash means n minus 1 dimensional of the real linear space. Solution. Okay. Now, it is clear. There is no doubt. According to the here, x and y, we are taking any two elements x and y on n dimension of this part, alpha being the real number. Here x equal to x1, x2, so on, xn, and y equals to y1, y2, so on, yn is there. Here the relation is transformation of x plus y equal to, that is transformation of x means x1, x2, so on, xn, y means y1, y2, so on, yn is there. Now it can also be written as transformation of x1 plus y1, x2 plus y2, and so on, xn plus yn. Now, again, this value is x1, x2, so on, xn. So, by the relation, transformation of x1, x2, so on, xn means that is the image of the relay from the relation x1, x2, so on, xn minus 1. So, again, this is x1 means x1 plus y1, x2 means x2 plus y2, so on, xn minus plus yn minus 1. Again, that can also be written as x1, x2, so on, xn minus 1 plus y1, y2, so on, yn minus 1 by the definition of vector addition to r power, vector addition in r power n minus 1. From the relation, this value is t of x, this value is in terms of y, so this value is t of y. That is, when the t of x plus y, from the relation t of x plus y equal to t of x plus t of y, that it must be satisfied here by the definition of t, and again t of alpha x equal to t of alpha of x means x1, x2, so on, xn. So, listen carefully. Here, according to the scalar distributes each and every one is there. So, that is alpha x1, alpha x2, so on, alpha xn is here. Again, this value is x1, x2. This is xn is here. So transformation of x1, x2, so on xn means alpha x1, alpha x2, so on alpha xn minus 1 by definition of t. So alpha being that is here, that is the common of this part. Here alpha of x1, x2, so on xn minus 1. So this is alpha into this value is t of x by definition of, okay, by definition of t. Now, thus, capital T is a linear transformation r power n into r power n minus 1. Hello? Can you hear me? Is this visible? Okay. Now, the relation is satisfied here. Okay. Now, some other problems are also practiced here. Here, the following the mapping from r square into r square. Now, that is also here the defined the mapping. Is it coincide given the relation or not? Say here, this is the 2 dimension of this part and image is also 2 dimensions. Okay. Image of the dimension is 2 and it's in the same manner. Now, these 3 problems, these three defined relations, is it linear transformation or not? Now, in the same manner, the following, the above examples, we must practice, okay? You must practice in the same above manner is there, okay? Now, students, listen carefully. These 3 examples are also for your practice purpose. There is no doubt, okay? Now, here one of the example, m simultaneous linear equations. Consider a system of m simultaneous linear equations in n unknowns of the form. Now, this is the matrix representation. Now, this is also just you have to receive that this is also referred in the matrices of the homogeneous system of linear equations. So here linear equations a11 x1, alpha 11 x1, alpha 12 x2, so on alpha 1n xn equal to b1. This is also simultaneous, m simultaneous system of m simultaneous linear equations in n unknowns. So here the constant values are b1, b2, so on bm, and variables are x1, x2, so on xn, and the representations of here x1, x2, so on xn, okay, and alpha 11, alpha 12, so on alpha n. This is the coefficient of the system. Okay, in the matrix relation is coefficient of the matrix. Now, from the system of defined a mapping, here alpha m1 x1, alpha m2 x2, so on alpha mn xn. Here n unknowns here and m be the simultaneous linear equations. Okay, now this is the defined of the r power n into this system referred defined the mapping is r power n into r power m because mn unknowns is here. R power defined the relation of the mapping is T maps. Now here that is n consisting of the variables that is r power n into r power m, that is the m image of the part. Okay, m dimension of this part. Okay, here x equal to, that is also referred here x being the variables of this here x1, x2, so on xn, that is the consisting of the vector is denoted by ax, n consisting variables here, that is also is in r power n, belongs to r power n, whatever it is. So here the transformation relation is T of x equal to b is here. Now the above the system of linear equations, simultaneous system of simultaneous linear equations, defined the relation is Tx equal to b. Okay. Now b means here by b1, b2, so on bm. Now this is also consisting m tuples of the real linear space. Now here the capital T is a linear transformation r power n into r power m is there. Now, this is one of the important example on differential operator. Okay, 3.3.5. Now, how to define the differential operator on linear transformation? Now, here given the real valued, the set of all real linear, L be the real linear space of all polynomials with real coefficients. Okay, defined on the interval is closed interval 0, 1. This is the square bracket. It read as closed interval 0, 1. That is the meaning of 0 less than or equal to x less than or equal to 1. The mapping T defined by, what is the mapping of the relation? Here on the set of all polynomials with real coefficients, T of P equal to on differential operator differentiating with respect to of P. Here P be the one of the polynomial. Okay. Now d by dx denotes the differential operator. Now at the same time that is also called denoted by capital D. Already we have practiced in UG first year and MSc Mathematics in the differential equations. According to that, here d by dx is called capital D. That is an equivalent to capital D. That is called differential operator, and the symbolic operator is there. Okay. Now here, now differential operator is also a linear transformation on L through this relation. That is T of P equal to dp by dx. From the real linear space, P of x be the one of the set of the polynomial. We are taking the one of the polynomial in the real linear space. The set of all polynomials, we are taking at least one of the polynomial is P of x. Here dp by dx is also a, now this is also, this polynomial is with respect to x is here. So this polynomial is also defined on the differential of a differential part dp by dx. So that the relation is also a polynomial. Okay, here we are taking any two elements, that is any two polynomials. P means P of x, Q means Q of x. So P of x and Q of x is also a linear space. Here alpha being any one of the real number. Now we will satisfy, there are two conditions, that is transformation of P plus Q through the set of all polynomials. D by, now define the relation is d by dx of, here enter the value, say x is there. So this value is, say z is there, dz by dx. Here z means P plus Q. From the defined relation is T of P equal to dp by dx. P plus Q. Again T of Q equal to dq by dx. T of P plus Q equal to d by dx of P plus Q. Again that can also be written as dp by dx plus dq by dx. Now dp by dx means from the relation T of P on the from the another relation replacing by Q, that is dq by dx means T of Q. And at the same time scalar multiplication is also satisfied and throughout the differential part. T of alpha P equal to d by dx of alpha P. That is alpha into dp by dx. Here alpha into dp by dx means T of P. That is, here clearly T is a linear transformation from L into itself is there. Okay, students, listen carefully. This is the through the differential operator relation. And again, one of the real valued function is here, T of f equal to integral 0 to 1 f of x dx. Another example is on integral part. Here L be the real linear space of all continuous real valued function defined on the closed interval 0 and 1. Here the mapping is defined by T maps. Okay, L into R. T defined the L into R. Here the defined relation is one of the set of real valued function is, say, that is f is there. F means T of f, that is the relation defined on integral of the part, because this is the real valued continuous function. So that's why we are taking on integral of the relation integral 0 to 1 f of x dx. Now in the same manner we are taking another function is g is there, T of g, T of h, whatever it is. T of g means integral 0 to 1 f of x dx. For here f being the real linear space on the domain of the part, and at the same time g is also real linear space on the domain, h is also domain on the real linear space of the part. Now this is also a integrable function. Integrability or the set of all real valued function is also a linear transformation through the real line or line integral of this part. Okay, T of g means integral 0 to 1 g of x dx. Now at the same time f and g belongs to L, f plus g is also belongs to L. That is the closure condition verified. At the same time, if it is a linear transformation, okay, T of f plus g equal to integral 0 to 1 f plus g of x dx. That is the practice purpose. So again, that can also be written as f of x plus g of x dx on integrable part. Integral 0 to 1 f of x dx means t of f. Integral 0 to 1 g of x dx means t of g. So condition is verified on linear transformation of the first condition. Second condition is, again we are taking alpha being any one of the scalar, t of alpha equal to replacing f by alpha f, integral 0 to 1 alpha f of x dx. So alpha taking it so outside of this part, alpha into integral 0 to 1 f of x dx. Again alpha into this value is t of f, so that is t of f. So alpha, t of alpha equal to alpha into t of f. That is also a linear transformation. That is the short answer question. Okay. The above example is a short answer. Okay. So already we have explained in the solution through this one. So finally, in examination, define linear transformation. This question is also given in sometimes is there. That is the simplest part. Now this is also under your undergraduate level. Okay. And now here in the, so that is also referred the vector spaces of this part. Okay. Now, how to given the question? Define, please note down, define linear transformation or linear transformation or homomorphism on vector space. Homomorphism on vector space. Show that the differential operator and integral function from the real linear space into capital R is a linear transformation. So differential operator and integral operator is also a linear transformation. Now that question is given in the final examination. That is also it completely depends upon the linear transformation definition. Listen carefully. Any doubt? Yes. According to the definition, transformation of x plus y equal to t of x plus t of y, t of alpha x equal to alpha into t of x. Okay. There are these two steps define the definition of linear transformation. At the same time, that is also called homomorphism on vector spaces. In sometimes it is also denoted by, now given the mapping is t from u to v, now ORR homomorphic f of u comma v. So homomorphism from u to v for the field capital F. That is HOM under base f of u comma v is there. Now here the defined the integral transformation, the differential operator part is also a linear transformation. So here see the example, that is 3.3.5, that is one of the solution already we are explained here. Okay, there is no doubt. And in the same manner, integral transformation, integral part. So how to define the integral? Just we are taking the one of the real line is there. So that real value, we are taking so many functions on the real line. F, G, H, there are so many functions. So these are all set of all real valued in the real linear space of all continuous real valued functions defined on closed interval 0, 1. Here when the initial point coincides with the terminal point, that is closed interval of this part. Okay. Now, here integral 0 to 1, that transformation relation defined L into R. T maps L to capital R. So, here integral transformation is T integral part T of f equal to integral 0 to 1 f of x dx is also a linear transformation. That question is also, sometimes it is given for the linear transformation of this part. Okay, students, just you have to see and observe this given this lemma. Let T maps, T defined L into L dash. So L be the one of the real linear space and L dash is the image of the linear space. So there are L and L dash, there are two linear spaces here. T maps L into L dash or T varies from L into L dash, whatever it is. So that the mapping is defined by, now we are taking one of the image, domain of the element is X. Here X belongs to L. That is transformation of X equal to image of the value is 0 is there. So T of X equal to 0 for all X being the domain of the value. So relation is verified here. X belongs to L and 0 is also belongs to L dash. So given the mapping of the relation is defined by T of X equal to 0 for all X being the L. So define the relation is also a linear transformation from L into L dash. Now these are all very simple on linear transformation. So sometimes the entire that paper is given for the definition of normal linear space and examples, and embed Banach space and examples, and at the same time embedded system. Okay, there are so many. Now it is very simplest part. And third one is the here third unit is for the linear transformation of the boundedness of the linear transformation. That's why now when you must thoroughly practice first according to the session, first 3 units are also well practiced, then automatically easily to achieve in the final examination. There is no doubt. Okay. Now here the defined relation is T of X equal to 0. Now here T is a linear transformation from L into L dash. This transformation is called zero transformation. Yes, zero mapping from the given the transformation identity and 0 is also a linear transformation. T of X equal to 0. So zero transformation is denoted by 0 cap. Now that is also theta cap is there. Now that is the 0 crown. It read as the 0 crown, 0 cap, whatever it is. Now, what is the difference between the 0 vector? Now, 0 vector means simply that is denoted by 0 bar is there. T of 0 bar equal to 0 bar crown. 0 bar crown is also image of the element. Okay. Now you are nothing but 0 bar and 0 bar crown. We are treating as 0 is there. So that's why we are defined from the relation T of X equal to 0. Now given the relation is also a linear transformation. It varies from L into L dash. This transformation is called zero transformation. Okay, zero transformation is also a linear transformation. According to these two conditions, here X and Y by any two vector linear space, any two vectors or any two spaces of the elements in linear space, alpha being the field element. So transformation of X plus Y equal to, this is what is the condition? T of X equal to 0. Again, this value is also T of X plus Y equal to 0. 0 means in addition of the vector. 0 identity is there, additive identity. 0 can also be written as 0 plus 0. Again, this 0 is T of X and this 0 is T of Y. And again, second condition is T of alpha X equal to is 0. Okay. Now this is alpha into T of X. So 0 can also be written as through the scalar alpha into 0. Again, this is alpha into T of X. So 0 transformation is also a transformation. In the same manner, 0 transformation and identity transformation is also a linear transformation from giving the relation, given the relation I of X equal to X. See this example. So this is the identity mapping. Here L varies from, okay, now I defined from L to L because this is the identity mapping. So identity mapping of the relation is I of X equal to X. So given the mapping is also a linear transformation. So in the same manner, we are taking I of X equal to X and Y be the one of the element in the real linear space of the domain, I of Y equal to Y. That's why I of X plus Y equal to X plus Y. X plus Y means, what is that? X means I of X, Y means I of Y. So that first condition is verified. In the same manner, second condition is I of alpha X equal to, this is alpha into I of X. This is also a identity 0 transformation. 0 and identity transformation is also a linear transformation. That question is also given in sometimes. Okay. So inverse of the image is called image of an inverse equal to inverse of the image. Already we have explained from the beginning of this part for the linear transformation, minus T of X equal to minus T of X. This is also a negative transformation is also a inverse of the image equal to image of the inverse from the defined of this part. defined the mapping T maps L into L dash. So negative transformation is also a linear transformation. So negative transformation, negative mapping is also a linear transformation. That's why we are explained here. Image means this is the T of X is the image of this part. So image of inverse equal to inverse of the image. That is now that can also be written as, given the relation is it read as image of an inverse equal to inverse of the image. That is also a linear transformation. So again, minus T of X plus Y equal to, so that is minus T of X plus Y. Again, that can also be written as minus of T of X plus T of Y. Here T of X means minus is also distributes. Minus T of X, minus of plus means minus, minus T of Y is there. Now, first through the negative transformation, first condition is verified for linear transformation. In the same manner, minus T of alpha X equal to alpha into minus T of X. So, minus T is a linear transformation. Okay, students, this is, listen carefully. Now, up to this content, okay, C and it is clear, it is clearly and it is observed here. It was observed here. There are important of this part. So 0 and identity part is also a linear transformation, and image of an inverse equal to negative transformation is also a linear transformation. Okay. And in the same manner, already we have explained, differential and integral part is also a linear transformation through the definition of linear transformation definition. Okay. Now this is one of the important concept, linear transformation of this part. Okay. So sum of any two transformations can also be written as, here there are two linear spaces here. L and L dash, there are two linear spaces over the same scalar field. Okay. The set of all linear transformations of L into L dash. Now, that is also a set of all linear transformations. There are so many transformations are here. We are taking, there are two transformations with respect to X. Now, defined of the part is the addition of two transformations. Sum of any two transformation is addition of individual transformations. Scalar multiplication also holds good. Alpha T1 of X is alpha into T1 of X. So here T1 and T2 both are linear transformations, and alpha being the field of the element. Okay. Please stay on the line. Please stay on the line. Okay. Now, this is, we are taking any two transformations, T1 and T2. So again, closure of the condition of the transformation, T1 plus T2 is verified. And at the same time, T alpha being the field element and T1, either T1 or T2, here the scalar multiplication holds good. Alpha T1 and again alpha T2 is also verified here. Both are linear transformations from L into L dash. So according to that relation, alpha, we are taking any two field elements or scalars, alpha and beta. And again, the linear space of the elements are X and Y. So T1 plus T2 through this condition, direct step. What is the condition? For the linear transformation, alpha X plus beta Y, that is the one step test for the subspace through the transformation is T1 plus T2 of alpha X plus beta Y. That is the direct condition on transformation of this part. That is T1. Now it can also be written as T1 of alpha X plus beta Y plus T2 of alpha X plus beta Y. Now that is the condition verified for linear transformation. So for the set of all transformations. In the same manner, T1 plus T2 plus T3. There are three transformations here, and up to n transformation is also here, but here the defined the mapping is L into L dash. Okay, we are taking in any two transformations through this condition, one step test for linear transformation, T1 of alpha X plus beta Y plus T2 of alpha X plus beta Y. Now this is again alpha into T1 of X plus beta into T1 of Y. This is alpha into T2 of X plus beta into T2 of Y. Now, this is the linearity condition. There is no doubt. When in the say above manner, here alpha of T1 of x plus T2 of x plus beta of T1 of y plus T2 of y is here. Now enter this relation is denoted by here T1 of x plus T2 of x can also be written as T1 plus T2 of x, T1 plus T2 of y is here. So again, this condition is verified for the sum of the transformation is also a linear transformation. And the scalar multiplication is, we are taking in any two elements in the real linear space and beta being the scalar alpha T1 of beta x plus gamma y. This is the gamma. Beta and gamma, this is not R. Students, please rectify this mistake. This is the gamma. Gamma being one of the scalar. Sir, beta and gamma, there are two scalars here. And according to this, alpha of alpha T1, we are taking the one of the transformation is alpha T1 of what is that? Here beta x plus gamma y. Now again, we are considering here beta of alpha T1 of x plus gamma of alpha T1 of y. So therefore, finally alpha T1 is a linear transformation. And in the same manner, the above example is verified here through the linear transformation. Now we will show that is it a linear space or not according to the above conditions. So L1 to L8 conditions verified from the first unit of this part through the linear space or vector space. So here first condition L1 is the above zero transformation is t plus 0 cap equal to t for every linear transformation. T plus 0 cap with respect to x. T means t of x. There is t of x plus 0 cap of x. This is the zero transformation. That value is 0. T of x plus 0 means t of x. So first condition is verified from the equality of mappings t plus 0 cap equal to t. So L1 holds good. L2 is image of the additive inverse. So minus t of x equal to, already this is the negative transformation is also a linear transformation. From that relation, t plus of, so transformation is applied through the vector under vector addition, t plus of minus t equal to 0 cap. So with respect to x, we must define for the mapping t of x plus minus t of x. Again, this is t of x plus of minus is minus t of x. So this value is 0 and this value is 0. So again 0 means 0 cap of x is there. So t plus minus t equal to additive inverse holds good. And in the same manner L3, L4 is there. This is the L3, L4 already. L3 is the scalar multiplication. Okay, abelian of this part from the abelian, and L4 is the scalar condition is there. Scalar multiple is there. Associative, sorry. L3 is the associative and L4 is the commutative is there. So there are two conditions are here. T1 plus T2 plus T3. Again, L3 is also there. So again, T1 plus of T2 plus T3 and T1 plus T2 of plus T3. So that is also when the left and the right both are equal. That is called the associative existence here. Now, here L4 is T1 plus T2 equal to T2 plus T1. Okay. Now that is the short answer question. Now here that is also you must practice here. So then the continuity part L3 and L4 you must write here. And what is the L5? Distributivity is there. And alpha of T1 plus T2 means alpha T1 plus alpha T2. So alpha scalar distributes under vector addition through under the for the linear transformation of the part. And again, alpha beta of T1 equal to alpha of beta 1. Okay. And again, L5 is also verified here. L6, L7, L8. Okay. Now we are taking a T1 plus alpha of T1 plus T2, alpha T1 plus alpha T2. Again, okay, T1 into 0 equal to 0 into T1 equal to T1. 0 is there. Okay. Now L8 is also verified here. L6, L7, L8 for the first year normal linear for the linear space condition. Now again, this is also one of the short answer question is given from you must write the continuity of this part and at the same time set off a linear transformation from L into L dash is also a linear space. Now first of all, given the relation through the set of all continuous linear transformation, is it a linear transformation or not? And then continuing to verify L1, L2, L3, L4, L5, L6, L7, L8. Now these are all mentioned from the beginning of this part for linear space to satisfying the linear space condition. Okay. Now at the same time, N1, N2, N3 conditions are also verified. Then automatically that is also a normal linear space. Okay. Now already we have you must define from the linear space definition to define the linear transformation. Okay. There is no doubt. So in examination, this question is also given. That is the very simple simple answer, and you must present the simplest part through the given the condition T1 plus T2 of x equal to T1 of x plus T2 of x, alpha T1 of x equal to alpha into T1 of x. Now, first of all, you must satisfy given this relation under vector addition and scalar multiplication. Is it a linear transformation or not? And the continuing of this part L1, L2, L3, L4, L5, L6, L7, L8. So these are all verified. Then automatically given the map T maps L into L dash is a linear space. That question is direct question is given in the examination. What is the boundedness? This is one of the important concept. Now this is the justification of the title here. Boundedness. What is the boundedness on linear transformation? Okay. First of all, let n and n dash, there are two normal linear space over the same scalar field F. Now here the defined the transformation is T maps n into n dash. So given the map, what is the bounded? Defined bounded linear transformation means T maps n into n dash be a linear transformation when it is bounded, if there exists any one of the real number is capital M be any one of the real number. That real number, that real number is the existence of this part, hence the condition of the transformation of the norm is norm T of x. We are taking the element is T of x. Norm T of x less than or equal to M into norm x. So here this is M be the real number. That real number must be existence defined the transformation of this part. So this is the norm transformation. So norm is defined on the transformation. So norm T of x less than or equal to M into norm of x. This condition is called boundedness. For all here, x being the domain of the element, here the domain of the mapping part is capital N. So that's why you are taking the values x belongs to N. In the same manner, y belongs to N is transformation of T of y less than or equal to M into T of M into norm y. Okay. So here M is called, that real number is called a bounded for T and okay, T. So here T referred to as a bounded linear transformation from N into N dash. Now when it must be continuous, it is continuous. What is the continuous of this part? Through the, already we know that one of the established property on continuous functions. What is the properties of continuous function? Every continuous function is bounded. Continuous function is bounded. But bounded function is not continuous. Already this is the established from the norm of this part. So then automatically then it is bounded. Okay. Here M be the bounded of the value. So already this is bounded of this from the transformation of the region. So then automatically then it is continuous. If it is continuous as a mapping, define the continuous linear transformation means continuous means it is a mapping of the metric space N into the another metric space N dash. Continuous is also depends upon the convergent sequence. Now we have, as you must assume one of the sequences here. There are so many students totally confused it. Okay. Now each and every definition depends upon the properties, and according to their properties, we must explain the converse of the part. There are number of times the entire mathematics must be surrounded of the part converse of the region. Okay. Converse of the regional part. So converse is also how to explain the converse. Sometimes converse is not true here. Okay. That's why already we know the property of continuous functions. A continuous function is bounded. A function which is continuous, then it is bounded. but bounded function is not continuous. Therefore, the converse of the theorem is not true. Now already we have practiced and we have see the undergraduation level in the real analysis paper. Now then the continuity part is also we must refer in the real analysis paper in the post-graduation MSc Mathematics second year paper real analysis. Now there is the continuing part of real analysis. Sometimes that is also DMS paper because some concepts are also well established through the real analysis. Now at the same time, and topology is also one of the analyzation of this part. In the same manner, another analyzation, continuity of topology. Now, one of the established analyzation part is functional analysis is there. Okay, there is no doubt. Okay, now here this is the continuous of this part and through the boundedness of the transformation. Then it is continuous as a mapping of the metric space capital N into the metric space N dash. How to define the equivalence of this property? We must assume one of the sequence in the domain of the part Xn be in one of the sequence, and that sequence converge to X. So sequence Xn converges to X, and again we must another assumption of this another sequence Yn converges to N is there. So depends upon the convergence condition, limit Xn equal to X, N is always approaches to infinite. So sequence is defined when the domain of the values are natural numbers and codomain of the real numbers is there. Okay. So here Xn of the limit point is X. So then the condition is mod Xn minus X is less than epsilon, or mod Xn minus X means that is the distance between the Xn and X. So the distance means that d of Xn equal to X is there. So sometimes that can also be written as there. So sequence Xn converges to X in N. At the same time, see that sequence is also converting into the image of this part, codomain of the part T of Xn sequence. That is the image of the metric space. T of Xn sequence in N dash. So this is the T of Xn sequence. So transformation is applying on both sessions Xn and X, T of Xn and T of X. So T of Xn sequence converges to T of X, that is in N dash. So here Xn converges to X in N, T of Xn converges to T of X in N dash. That is the continuity condition from the metric space capital N into another metric space N dash. That is the simple concept. There is no doubt. Okay. Now, according to this condition, students listen carefully. If you have any doubt, please contact us and personally some other examples. Some other examples I will give in through the WhatsApp. Now here there is no doubt. This is the under UG level. Okay, there is a lower session of the practice here. Convergence condition is okay. So it referred as Xn converges to X, or Xn converges to X, or Xn approaches to X, whatever it is. So these are all domain of the values. So that is Xn and X. They both are all in these values are Xn is one of the sequence that convergence point is X is there. So these are in metric space N is there. So transformation is applying on given this condition. Simply it referred as T of Xn to T of X. Now both values are is in another metric space N dash is there. So that is the continuous condition. Okay. Now according to that condition, we have to practice one of the important theorem. This theorem is very, very, very important in the final examination. So many times it is given in the bounded linear transformation of this part. Now this is the either second essay or third essay, whatever it is, T of Xn. Okay. That is the transformation of the part of the boundedness. Here that is the 3.4.1 through the continuous linear transformation. Okay. Now what is the theorem? Let T be a linear transformation. Now here T maps T maps N into N dash. N and N dash both are normal linear space, and the T be the linear transformation defined linear space N into another linear space N dash. So that defined the linear transformation of the part is given the conditions are equivalent. What are the conditions? Here, when the first condition is T is continuous, already condition is here. Continuous condition is here. Xn converges to x in n and T of xn converges to T of x in n dash. And according to the relation given now this condition is called continuous of this part. So one is equivalent to second condition. 1 implies 2, 2 implies 3, 3 implies 4 and 4 implies 1. So T continuous. Now we will prove that T is continuous at the origin. Origin means xn approaches to 0. This is in capital N. T of xn converges to T of 0 means 0. That is the 0 transformation. That is also in n dash. Another, from the continuous at the origin means this is the condition. There exists a boundedness of this part. A real number m is greater than 0. So, continuous at the origin, we will prove that T is bounded. Boundedness means already from the beginning of the definition of bounded transformation, norm T of x less than or equal to m into norm of x for all x belongs to n. That is the boundedness condition. So, that is transformation is bounded. And again, this is the open sphere part. Okay, given the closed unit sphere, how to express the closed unit sphere? This is less than or equal to. Suppose it is less than 1, given the norm, that is the open sphere of this part. Already this is the boundedness. So bounded means through the closed part is there, closed interval is there. So this is the closed unit sphere. Okay. Capital S equal to set of x being any one of the element. That element is in n. And that element of the norm is also less than or equal to 1. That is the given the closed unit sphere in n. Then the image of the part, image of the closed unit sphere is T of S is also bounded in n dash. From the closed unit sphere of the set is in n. Then the image of the closed unit sphere is also in n dash. So image of the closed unit sphere is T of S. Okay. Now there are 4 properties here. 1 implies 2. Let T be continuous. First of all, so what is the continuous condition? First of all, we are taking the T be continuous. That is the first condition. So we must assume one of the sequences xn be any one of the sequence. That sequence in n, xn converges to 0 as n tends to infinity. Again, since already given the part is T is continuous, we are applying on both sides the transformation. T of xn converges to T of 0 equal to 0 as n tends to infinity through the definition of continuous. Now this is in n dash. So T is continuous at origin. This condition is called T of xn converges to 0 means that is the T continuous at origin transformation. Again, 2 implies 1 because 1 is if and only if second one. So 1 implies 2, 2 implies 1. And according to the T continuous at origin, that is the first assumption. And through this one, we assume any one of the sequence, xn be the sequence in n, such that xn converges to x for all x belongs to n. And then we have, this can also be written as xn minus x converges to 0. Applying on both sides by x, that is also subtraction of this part from the sequence. Xn minus x converges to x minus x. Directly, we are taking in here. So, according to the property, we are taking the minus x is there. X belongs to n and minus x is also belongs to n. That is the algebraic condition. Additive inverse is also exists because x is being the non-zero of this part. So, additive inverse is this. Applying on both sides, minus x is there. Xn minus x converges to x minus x is 0. Now, this is the condition. Now, that is xn converges to xn minus x converges to 0. Applying the transformation T of, because T continues at the origin, T of xn minus x converges to 0. Okay. Now, there is the linearity T of xn minus T of x converges to 0. Now, that can also be written as adding on both sides T of x, T of xn minus T of x plus T of x is 0. And again, converges to T of 0 plus T of x means T of x. Directly, this is not converting into this side. Okay. That is not correct here. We are applying on both sides and adding on the plus T of x. Okay. We are taking the plus T of x on both sides. Finally, we are getting the T of x and converges to T of x as n tends to infinitive, and according to this is xn converges to x. So this is called T is continuous at x. So 1 if and only if 2, that must be satisfied here. And in the same manner, 2 if and only if 3. So first of all, 2 implies 3. We are taking it T continuous at origin. Suppose third condition is we will prove that T is bounded, but start in the preliminary part, T is not bounded here. That is our assumption. So any positive integer n is there. Here xn being any one of the element, that element is also belongs to capital N. So we are applying through the condition T is not bounded means norm T of x is greater than or equal to. So norm replacing x by xn is there through the sequence. Norm Txn is greater than or equal to n into replacing x by xn. So in the above definition of the bounded, replacing capital M by n is here. And because this is not bounded means we are treating we must, given the condition is greater than or equal to. Okay. So dividing on both sides, n into norm xn. So norm T of xn, norm A by norm B means norm A by B. So that is norm T of xn by n into norm xn is greater than or equal to, this is the unit square, equal is greater than 1 is there. So just like that, this value xn by n into norm of xn, that value say, that is yn. That is our assumption. Okay, xn by n into norm xn means that value is y. So norm Ty is greater than 1. Yn is greater than, yn equal to 1 by n is here. Because limit 1 by n means limit 1 by n means that the value is 0 because n approaches to infinitive. So that's why norm yn is also converges to 0 as n tends to infinitive. Because yn converges to 0 means as n tends to infinitive. So applying on both sides the limit 1 by n is always approaches to 0, limit 1 by n equal to 0. But the sequence of the norm T of yn sequence does not converge to origin. Because norm T of yn is greater than 1 is there for every n values. So this shows that T is not continuous at the origin. So that is the contradictory part. Okay. Suppose T is not bounded, that is the contradiction, means that it given the transformation is bounded. Okay. So again 3 implies 2. We are taking the boundedness of this part and we will show that given the transformation is continuous at the origin. Boundedness condition is here. First of all, to write the boundedness condition. So we will show that T is continuous at the origin. We are taking any one of the sequence here. Xn be any one of the sequence belongs to n, and again xn converges to 0. Okay, a continuous function, it follows that applying on what about the condition? Norm continuous condition is norm xn converges to norm 0. That value norm 0 means 0. From the inequality of the from this unit, okay, norm T of xn is less than or equal to, replacing x by xn is there. Norm T of xn, this is the first equation. From the first equation, we have norm T of xn less than or equal to m into norm xn. So norm xn converges to 0 as n tends to infinitive, automatically this is also converges to 0. So T of xn converges to 0 means as n tends to infinitive. This condition is called continuous at the origin. Again, we must prove that 3 if and only 4. First of all, 3 implies 4. T be the bounded. So fourth condition is closed unit sphere. So there exists be any one of the positive real constant capital M is there, and norm T of x less than or equal to m into norm of x. Okay. Now that is the bounded condition. From the bounded condition, that value m into norm of x means that value is less than or equal to m. So we are getting the norm T of x less than or equal to m. So this condition is transformation of S is bounded because this is the boundary value is depends upon the closed unit sphere. Okay. And first of all, here the closed unit sphere of the part, the transformation is also bounded. So T of S be bounded. And what about the third condition? S is bounded. T is transformation is bounded. That is, we will prove that T is bounded here. There exists a positive real number, m1 be any one of the positive real number, transformation of t of x less than or equal to m1 and put x equal to 0. Therefore, 0 is less than or equal to m1 into norm x. So x by norm x is also in capital X because here x is non-zero is there. Okay. So if x equal to 0, directly given the condition holds good. X not equal to 0 means x by norm x is in yes. So norm of t of x by norm x less than or equal to m1. Replacing x by norm x. So norm of transformation of x less than or equal to m1 into norm x. So given the transformation, this is the closed unit sphere part. So again, given the transformation is bounded from the first, second, third, and fourth equations. These are all equivalent of this part. This theorem is very important. There is no doubt. Students, listen carefully. The above theorem of the boundedness is equivalent to the continuity of the transformation capital T. So continuation of the transformation T, all the conditions are verified here. So boundedness and continuity both are interchangeably. In the case of linear transformation, from the first condition, given the transformation is bounded, then automatically from the closed unit sphere of the transformation is also bounded. So that is supremum of norm t of x. That is norm t of x is always greater than less than or equal to 1. That is also a finite. So the norm of the bounded linear transformation means norm t equal to supremum of norm t of x. Now these are all one is interlinked to another one. So this value through the norm condition of the transformation, through the norm transformation, so norm t equal to supremum norm t of x, therefore norm x is less than or equal to 1. So given the normal linear space is denoted by n, so that is non-trivial of this part. Okay, say this is the second equation. So norm can also, how to define the norm in various parts. So already we have defined the norm condition is there from the boundedness part. So 3.4.1, let us, you have to see this here from the above theorem. What about this one? Norm t of x less than or equal to m into norm of x. That is for the boundedness of this part through their norm. And here the second condition is then when the transformation is of the closed sphere, that is also bounded. So that is supremum norm t of x. Here norm t of x less than or equal to 1 through the closed unit sphere. So that is norm t means supremum on the defined on the norm of the supremum of their norm. So norm t equal to supremum of norm tx. This is also another norm. So norm can be divided into different norms through the transformation. So given the normal linear space is non-trivial, this is the second condition of the norm. And third condition is norm t equal to supremum of norm tx. Particularly here the transformation of the norm must be equivalent to 1. There is no doubt. Here the from the closed unit sphere is less than or equal to 1. That is the second condition of the norm. And third definition of the norm is on the supremum of this part, norm t equal to supremum into norm t of x. But here the transformation of their norm must be 1. That is an equivalent to 1. That is the third one. Where if it is not equal to there, x not equal to 0, and according to the above theorem from the continuous properties, first one t is continuous, okay, and second one continuous at origin, third one t is bounded, fourth one closed unit sphere. Okay, now what about the fourth condition? In the above theorem, closed unit sphere, then the image is also bounded in n dash. Okay, there are one is equivalent to another one. Now this theorem is very important, especially in this unit. That is a bounded linear transformation. Okay. Now in the same manner, okay, norm t of x. If suppose x equal to 0, theorem holds good. Okay. Now here the different norms is norm t equal to, that is x not equal to 0 means the supremum of norm t of x by norm x. These are all well established in the above theorem. And to explain the different norms, suppose according to my sense, how to give this question? Okay, define linear transformation and defined bounded linear transformation and explain their norms through the continuous linear transformation, continuous properties. So you must present the first of all, you must present the answer is, what is that? Bounded linear transformation definition. So norm Tx equal to m into norm T of x. Okay. First of all, linear transformation and their boundedness. And according to this theorem, norm T of x less than or equal to m into norm of x. Second one, norm T equal to supremum of norm Tx, norm x less than or equal to 1. Norm T equal to supremum of norm Tx from norm T of x equal to 1. Suppose x is non-zero, so norm T equal to supremum into norm T of x, norm Tx by norm x, here x being the normal linear space. Here norm T equal to, this is the supremum of this part. From the infimum of this part, m is greater than 0, that real number is greater than 0, norm Tx less than or equal to m into norm of x. That is the greatest lower bound of this, greatest lower bound of their norm. So that is called infimum of this expression. Because through the boundedness, through the bounded, how to define the bounded? Now already we have defined in the lower classes, bounded definition is there. Okay. Now according to that, okay, according to that, lower bound and upper bound, okay, lower bound, when a boundedness means any non-empty subset of the real number, which is a lower bound and upper bound, either bounded above, or bounded below, or bounded above. So bounded below of the aggregate is called lower bound, bounded above is aggregate is called upper bound of this part. And through the according to the boundedness definition, now there are so many theorems are explained here in the undergraduate level. Okay, continuous function is every convergent sequence is bounded, but bounded function is not continuous. Students, listen carefully. One is interlinked, another one from the lower section of this part. Now, each and every one much more useful for the continuity of the theorems. So, just you have to look at, observe here in the lower session, what is that? Convergent sequence definition, divergent sequence definition, properties of convergent sequence, and through the convergent sequence defined by Cauchy. Now your assumption xn and xm, there are two sequences are here. That is norm xn minus xm is less than epsilon, epsilon by 2 plus epsilon, that value is less than epsilon is there. For all n and m both are being the positive integers. All the positive integers are here, especially that is the natural numbers of the part. Now, according to the lower bound and upper bound, and through the real line of this part, a real line of the boundary values explained by Riemann. So that is the Riemann concept. Okay, and according to the Riemann integral or integrable of this part, so this is also a integrable function is also a integral operator is also a linear transformation. Differential operator is also a linear transformation. That is one of the important session. And in the same manner, zero transformation and a negative transformation and identity transformation is also a linear transformation. Now, hence the continuity of the part, that is the continuous function. What is the continuous function? Already we have defined the continuous condition is there. And in the lower class, that is the real analysis part is there. Real functions, limits and continuity is there. So according to the continuity, now we have explained the boundary conditions. That is the supremum and infimum of the value. What is the supremum? Least upper bound of the norm transformation. Now here infimum is greatest lower bound of the norm transformation. Through the norm, how to define the transformation? So norm x is also introduced. Already we have introduced in inner product space of the part. So that is norm x equal to square root of inner product of x and x. That's why here the particularly norm can be divided into so many regions are there. Particularly here bounded linear transformation. What is the bounded linear transformation? And here norm T of x less than or equal to m into norm of x through the norm. And second one is, again, number of times I explained here, and this is also one of the research content, especially in functional analyzation. Okay. So This is the, of course, you are one of the postgraduate. Now, when you must understood the enter the analyzation of this concept, analyzation can be divided into one is interlinked to another one. Enter through the entire the analyzation, it completely depends upon the some other properties, algebraic properties, and boundedness session and interval session and Riemann integrals concept. Okay. And at the same time, for functional differentiation, functional integration. Okay. So, according to the Riemann concept, he must another kind of constant function is also developed. That is also one of the error is there. So that is that mathematician is Stieltjes. So according to that, integral is called Riemann-Stieltjes integrals concept. So the entire these are all research contents in particularly in analysis part. Okay. Now, how to define the particularly norm? Norm is also one of the research content. So this is norm t equals to supremum into norm t of x and norm x less than or equal to 1. This is completely elaboration of the norm is there. Norm concept is there. There is no doubt. Okay. Particular how to define the norm. So just you have to take the one of the vector space is there. From the vector space, you must develop the continuity part in an inner product space and some other inequalities. And through that, Minkowski inequality, Holder inequality is also verified. And according to their inequalities, to define the norm and a linear space. So now let us introduce the part of normal linear space. So through the norm is norm t equal to, this is one of the norm supremum into norm t of x. Okay, students, norm x is less than or equal to 1 is there. Okay. So number of students, please students listen carefully. Already you are asking one of the doubt is arised here. Okay. Sir, what is the use of this one? Okay. And according to enter the analyzation concept, this is the regular life. Now, enter the analyzation, you must utilize it in the regular life, and so many research contents and engineering concepts are also there. Now, this is also under the civil engineering concept, civil engineering, and also one of the now latest the technology is there. Artificial intelligence is also introduced through the norm is there. Okay, there is no doubt. How to, sir, what is the use of, how to connect it with the artificial intelligence, AI and functional analysis? Okay, this is also one of the research content for your, especially for your purpose. Is it regular students or non-regular students or not? There is no deviate here. That is none other than the students. Each and every one, you must thoroughly practice the analyzation concept. One is connectivity to another one, and through the properties and the lemmas are also there. Now, Rayleigh theorem, Lagrange mean value theorem, Cauchy mean value theorem, Taylor theorem, and Maclaurin series. Now, these are all connectivity is there. Now, this is also connectivity in OR level. That is the operation research level. Through the operation research, now that must be developed through the computer techniques. So without operation research, without OR, we can't imagine the technology. Okay. Now, according to the operation research, now we have to introduce the operator theory is there. So, functional analysis and operator theory both are interlinked is here. So, when you must understood thoroughly and practice the each and every definition and the theorems in the functional analysis, and at the same time, operator theory is also well practiced. There is no doubt. That is one is another bonus of paper is functional analysis and implies operator theory. Okay. Now, there are another norm is here. Let us have to see here. Norm t equal to supremum of norm tx by norm x. Here, x being the n and x is the non-zero of this part. Now, at the same time, here norm t equal to infimum of the relation. This is another boundedness, greatest lower bound. Here, m being one of the real number. That real number must be greater than 0. Norm tx less than or equal to m into norm x. Here, x being x belongs to n. So, here alpha, beta, gamma. There are 3 numbers on the right hand side of this part. That is the third condition of the norm, fourth condition of the norm, fifth condition of the norm. There are not only their conditions. Now there is one of the norm is there. That is similar norms are there. Okay. Now here third condition is alpha, fourth norm is beta, fifth condition is gamma is there. Okay. Now, don't deviate here. Okay. Particularly, those norms are denoted by alpha, beta, gamma is there. So, norm T, especially norm T is an equivalent to one is equivalent to another one. Alpha equal to beta equal to gamma is there. Okay. Okay. Now, from the closed unit sphere, X is defined from norm X equal to 1. This is called unit sphere. Now, this is called a unit sphere. It is a subset of the unit ball. Unit sphere or unit ball, open ball or open sphere. Okay, whatever it is. It is completely based upon the interval of the system. So, in the closed sphere means what is the sphere? A set of points in space which are at a constant distance. Particularly, you have to observe in the three-dimensional part, we have introduced that is the spherical part of the part. Okay, spherical region or spheres. Okay, especially in 2 dimensions, that is called a circle. Okay, now here according to the it is an interval of the nature. Here unit sphere is denoted by X is defined from norm X equal to 1. That is called unit sphere. This is also one of the subset of the unit ball. That is also, ball is particularly defined. It is also less than or equal to 1. So here X being any one of the element. So that element is norm X less than or equal to 1. So sphere, according to the definition of a sphere, a set of points in space which are at a constant distance from the fixed point is called a sphere. So here the constant distance is called the radius of the sphere. Fixed point is called center of the circle, center of the sphere. Okay, and according to that unit ball, those norms are referred as supremum of those normed conditions, supremum norm T of X from norm X equal to 1, this value supremum alpha equal to 1. Yes, there is no doubt. Here norm T of X from norm X equal to 1 means this condition is alpha. Here alpha less than or equal to supremum of norm T of X from norm X less than or equal to 1 through the unit ball. So alpha is less than or equal to norm T. That is another condition. Yes. Already we know that given the condition T is a linear transformation, we can write norm Tx by norm X equal to enter the individual of the norm in numerator and denominator, and it referred, now that must be referred double mod of the value. So norm is double mod of the expression. Here norm A by norm B means norm A by B. And in the same manner, we are applying in the norm condition through the transformation norm Tx by norm X equal to norm of T by X by norm X. That is the unit ball of the nature. Okay. Now beta expression, how to define the beta? Now in the examination, in my sense, how to give in this question? Explained the norm conditions is on briefly part. Okay, is on briefly. How to define the alpha, beta, gamma through their norms. This is also one of the question. Suppose when you must understood the enter the concept of functional analysis, thoroughly you have to practice it, especially in the bounded linear transformation. Now, then automatically you must present in the paper is there. There is no doubt. There are through the alpha, beta, gamma, we have to explain this is also automaton theory is there. Okay. Now, alpha, beta is the supremum of norm T of X by norm X. Okay, students. Now, how you must think and elaborate the subject is personally part now to develop enter the concept of bounded linear transformation for the subject point of view. Okay, here beta equal to supremum of norm T by T of X by norm X, here X being the normal linear space element and here X being the non-zero of this part. Okay. Now, when you must here from the unit ball, X by norm X means X being the normal linear space. Here the denominator, given the denominator of the norm, X is non-zero. Non-zero means inverse exists. Then automatically X by norm X is denoted by X dash. Here X dash belongs to N and norm X dash equal to 1 is there from the definition of beta. From the X being the non-zero of the element through the beta definition is a supremum of, this is one of the norm T of X by norm X. When the closed unit sphere, unit ball of the part, supremum of norm Tx equal to norm x equal to 1, and we are applying here supremum. The definition is from the relation supremum of norm T of x by norm x. So alpha is an equivalent to beta. In the same manner, norm T of x gamma is also there. From the definition of gamma, this is also one of the norm. Norm T of x less than or equal to gamma into norm of x, and norm T of x less than or equal to gamma into norm x. So this is beta is greater than or equal to, so dividing throughout by norm T of x here, that is beta is greater than or equal to norm T of x by norm x. So finally norm Tx is less than or equal to, when the cross multiplication of this expression by CMR. CMR means cross multiplication rule. That is the simplest part. Okay. Norm Tx is less than or equal to means it cannot exceed norm x into beta is there. At the same time, beta into norm x. How to define the norm T of x less than or equal to beta into norm x? Now, you must write the from the top to bottom here. Okay. Now, gamma being the smallest of all real numbers, beta, yes, it's satisfying the one of the inequality is there. Now, just you have to see this inequality, norm T of x less than or equal to beta into norm x. Now, this is the entire, the concept is not, you should not present the, you should not present on the paper. You must thoroughly, you have to practice here. Okay, just you have to attempt only on the paper, that is only one time is enough. Now, thoroughly, you must imagine elaborate of the subject. Okay. Now, norm can be, how to define the norm in various manners. Okay. Gamma less than or equal to beta is there. Yes. Now, in the finally, norm T of x less than or equal to gamma and norm x less than or equal to 1 and norm T equal to supremum of norm T of x. This is norm x less than or equal to 1. Enter this concept is gamma is there. So, just you have to see and observe these relations. Now, one is here. Just you have to see and refer here. That is alpha less than or equal to norm T and alpha equal to beta, and at the same time norm Tx less than or equal to beta into norm x, and at the same time gamma less than or equal to beta. These are all depends upon the norm definition. Okay. Now, these relations and they especially, and fourth one, and this condition norm T equal to alpha beta. How to prove that norm T equal to alpha equal to beta equal to gamma? This is also one of the question is given. Okay. When you must thoroughly practice each and every one, then automatically easily to give the and easily to approach this answer. Okay. Without direct questions is not given here. Okay. Suppose paper, if it is paper is in an indirect part, then how to, now this type of question is given. Norm condition is an equivalent to norm transformation equal to alpha equal to beta equal to gamma. This question is given. Now, norm Tx less than or equal to norm T into norm x, and inverse of the transformation, identity transformation is in a multiplicative identity through the normal linear space. So, T inverse of T is identity is there, and at the same time T inverse T transformation is also a T maps T defined n into n dash, then inverse transformation is also a n dash to n is there. So, what is the inverse transformation or inverse mapping? How to define the inverse mapping? Suppose given the transformation is T defined from n into n dash. What is the T inverse? Now, that is n dash to n is there. So, T inverse of T of x equal to x. Here, x being the n is also a linear inverse transformation is also a linear transformation. Already, this example is also practiced here. Okay, there is no doubt. Okay, students. Now, see this one of the theorem. This theorem is very important. See here. N and n dash both are normal linear space. T be a linear transformation of n onto n dash. Yes, given that linear transformation defined on n onto n dash, now this transformation is 1 to 1. 1 to 1 means 1, 1 and onto is there. So, when the given the transformation is 1 to 1 and inverse transformation is also at the same time, it is bounded. Now, if and only if a necessary and sufficient condition in between bounded 1, 1 onto bounded. there is a positive one, you must, we will prove that there is a positive real number, m into small m be the infimum of the value. Capital M is the supremum. That is the basic expression of basic concept of enter the real analysis. Okay, M be the lower bound and capital M be the upper bound of the expression, or small m and capital M referred in Riemann-Stieltjes integrals concept, infimum and supremum is there. So that boundary value is also denoted by small m into norm x less than or equal to norm tx. Okay, this is the if and only if necessary and sufficient